Hi everyone, my name is Andriy and welcome to the CoffeeJUG online. Today is an interesting talk from Igor Braga, his software developer at IBM. And today we will talk a lot of interesting things about garbage collection in Java. So welcome, and let me just briefly explain who we are and why we are doing this. First of all, let's highlight that the main point we are here is a community. It's our 19th event and we have about 500 and more participants. Right now we are even like do not pretty follow by this counter, but we know that it's increasing, that it's like great things. So community is really our value and we are happy to like connect people from our local area as well as global areas and have a strong and healthy people around us, be in this atmosphere and connect people, like share our experience and invite amazing worldwide known speakers. So yeah, that's about our value. Here are organizers. Everyone is here. Ira, Igor, you don't see them, but our team is here. And a lot of thanks to our program committee, Olesa and Oleksiy, people who do a lot to find speakers, to help young speakers, to do a trial runs, and actually care about our quality. Also, a lot of thanks to our sponsors, Avenga and Sombra. Thank you a lot to making it happen, to support our community, and you really do your commitment to grow great engineers. Also, thank you to JetBrains, our community partner, and everyone who will fill the feedback form that you will get right after this event. You will have a chance to get the free 1-year license for almost any of popular JetBrains products. Great opportunity, thank you for this. So follow us in Twitter, Facebook, also we have a new Telegram channel. Enjoy this talk. Right now we will switch to the maintenance window for a couple of seconds and then Igor will make his talk. Thank you. Okay.
Sounds good.
Cool.
Hello, everyone. Good morning, good afternoon, good evening from wherever you are. You probably 7 p.m. most likely. I've just had my breakfast, so so welcome to CoffeeJUG on this section where I'll be sharing with you some really cool stuff about garbage collection, which is in my area. So I'm really happy to share this with you. So let's get started. So this just an important disclaimer saying this slide is just for information purposes. So don't make any hash decision based solely on these slides. Okay, this is the outline of what we're gonna talk to you about today. Some really quick garbage collection review. Then I'm gonna go through the different algorithms from the perspective of OpenG9. And at the end, I'm gonna share with you a really cool technology that we have here called double mapping arraylets. Cool. So if you want to play with all these different technology algorithms, GC algorithms, I encourage you to go to Adopt OpenJDK. Here you can get both Hotspot and OpenG9, and I encourage you to get both and play around with them and see like which one works best for you. So OpenG9. So OpenG9 is a fairly mature project. It came to the Open 2017. And a fun fact about it is that it started as an embedded JVM. If you heard about the Java Macro Edition, that's how OpenG9 started. It's an open community, open source project, so we welcome any contributors. It's pretty cool. All right, now to what matters, garbage collection. So this is a by the book definition, right? Garbage collections are for automatic memory management. The garbage collector attempts to reclaim memory occupied by the objects that are no longer in use by the application. That's opposed to other programming languages like C++, where the developer has to manually allocate and deallocate memory, like malloc, free, that kind of thing. Some of the responsibilities of the garbage collector are it allocates memory, identifies the liveness of data, meaning all the data that's not live is going to be considered garbage, therefore it's going to be reclaimed by the garbage collector. There are some positives for garbage collection, right? It's an automatic memory management, and it helps reduce the categories of bugs like dangling pointers, double freeze, so it's really nice. But on the other hand, we have some negatives. It requires additional resources, extra CPU cycles, more memory, right? It can cause unpredictable pauses, the famous stop the world pauses, and may introduce runtime costs. Application has little control of when memory is reclaimed because even though you can type system.gc, that's just a hint as to when GC will be triggered. So here are some of the different GC algorithms out there, and I'll try to walk you through each of them through the OpenG9 different policies. The only one that I'm not going to explain is reference counting, but it's a very simple algorithm. So reference counting is pretty much a GC algorithm that counts the number of references of an object, right? So say I'm an object and two other objects are pointing to me. So my reference count is going to be 2. So say after a while, these 2 references got deleted. So now my reference counts at now 0. Now I can be reclaimed by the collector. So it's very simple. That's reference counting, 30 seconds there for you. Cool. So some of the policies that are going to go with you today. The first one, Throughput, is one of the simplest policies out there. Stop the world parallel collector. And I'm going to walk you through GenCon, is a generational copying collector. Then an improvement upon generational is GenCon CS, Concurrent Scavenger, which is a pauseless collector. Pauseless, you're probably familiar with all the pauseless collector like ZG, Shenandoah, right? And the last 2 there are both Metronome is incremental software time collector and Balance a region-based collector. So that's what we are going to be doing today. So let's start with the first one, Throughput. So Throughput is a really simple collector. All these operations are completed in parallel, meaning multiple DC threads are collecting the heap, and they are all stop the world, meaning the application threads are not running while the GC is running. These operations are mark, sweep, and option compaction. I'll tell you what those are in a moment. And there's a native memory overhead for the mark mapping work packets because GC needs that to keep does its work a little bit better. So normally, whenever your application runs, right, GC allocates a contiguous block of memory. That's not always true, but most of the GC policies is going to use a contiguous block of memory, and that's what we call the heap. But for Throughput, divide this into 2 logical spaces, small object area and large object area. Most objects are going to be allocated in small object area. If an object is larger than a certain threshold, we put that in a large object area. So this is how an application behaves under the Throughput policy. So in the white arrows, they represent application threads, and the red arrows represent GC threads. So here, whenever an application thread depletes the heap, allocates everything that there is to the heap, then we're going to stop all the application threads, and then we're going to trigger a GC collection. That's going to be stop the world, parallel collector, multiple GC threads collecting the heap. Once that's done, we can let the application run as well. Once it depletes the heap again, then we trigger another GC cycle, and so on. So very simple. Stop the world pauses there, collecting the heap in parallel. So here, the this policy is divided into three phases. Marking, where we find all the live objects. We go through the object graph, starting from the roots, and we go through all the live objects. After we find that, we sweep the heap. So we claim memory for that objects, meaning all those objects that wasn't marked, it's considered garbage, so we sweep that. So at the end of the sweeping phase, we're going to have a linked list of free regions in the heap. And then we have a compaction phase at the end, because as the application runs, the heap can get fragmented. So what does that mean? So imagine the application is running, we have a bunch of GC cycles. At some point, your GC is going to look something like this, like a Swiss cheese, a bunch of small free spaces, but not enough contiguous space to allocate an object. So what can we do? We do a compaction. So we take all these live objects and compact to a certain portion of the heap, and then we have all this free space, contiguous free space that we can work with to continue the application. And as you can imagine, compaction is very expensive, therefore we try to avoid that the most. Now GenCon. GenCon is an improvement. Here we have a generation copy collector. Here now object is going to have ages. So it provides a significant reduction in stop-the-roll pauses times and introduce a write bear, because here we're going to be actually marking objects concurrently with the application. And before we were doing that, we were just doing everything stop the road. Here, we're going to be marking the objects concurrently, and we do need a way to see that. And we do have a concurrent global marking phase, which is this is the concurrent marking, which I'm going to go through with you in a moment. So instead of dividing the heap into small object area and large object area, here we divide the heap into nursery and tenure. In other words, nursery is new space and tenure is old space. We further divide the new space, nursery, into two logical spaces, allocate and survivor. All the objects are put in allocate space, and once we deplete that, we copy everything to survivor. That's what we call the scavenger, which is a copy collector, which is copying objects from allocate to survivor. And you might ask, like, when are we going to collect tenure, the old space, right? That's where global marking phase comes in. And every once in a while, we're going to trigger this global marking phase where we mark the tenure portion concurrently. And then at the end of this marking, we sweep the tenure, similar to Throughput. So this is how a GenCon behaves under this application behaves under GenCon policy. So we start the application, and once we deplete the allocate space here, we trigger scavenger, which is the copy collector. So here we're going to be copying all the live objects from scavenge space to survivor. That's all scavenge is doing, and stop the roll. So there we have another scavenge, and at some point we have a global start, global end there, and that's where we're going to be collecting the tenure space. And we do that because at some point tenure space can get very large, so we need a way to collect that, right? So global phase is going to be doing that concurrently, and then at the global end we're actually going to be sweeping the tenure to collect those objects. So write bears. So why do we need that? So imagine we have the following operation, right? We are trying to modify a field of an object like that. So let's have this object graph as an example. So there's this notion of three-color abstraction, which is supposed to be white, gray, and black. But here I changed the colors to green, yellow, and red because I think people kind of understand that better. So green means the GC thread has already processed that object. Yellow means GC is of processing that object, and red means the GC hasn't visited that object. So here in this example, GC has already processed objects, the roots, and object A is in the middle of processing object B and hasn't visited C yet. So imagine GC is marking objects while application thread is running. So imagine application thread comes along and deletes the pointer from B to C and adds a pointer from A to C. And then GC comes along and is going to be, okay, B doesn't have any children, therefore I'm done with B. So this is my resulting object graph where I have A, B, and roots that are marked. C is not marked, therefore I'm going to collect C. But as you can see, C is reachable from the roots, which is reachable from A. Therefore, if I collect that object, then something bad is going to happen. So we need a way to avoid this. That's where right barriers come in. So instead of having just a simple set field like that, we need to check, is a concurrent GC active? If there is, we're going to dirty that card. That way, at the end of the GC, we can go to those dirty cards and remember those objects that we might have forgotten otherwise. But we do need another write barrier. Imagine we can have references from the old space pointing to objects in the new space, and just the copy collector, the scavenger alone, cannot keep track of these old space to new space references. Therefore, we need another write barrier for this, and this is a really simple one. We just check if A is in tenured, meaning A is in old space, and C is not, meaning C is in new space. If that happens, then we remember A as well. Since we have two barriers here, we just put that in the same check, and then we can just save some CPU cycles there and have two barriers into one. Cool, so that's GenCon. Now let's go a step further and improve upon GenCon. That's Concurrent Scavenger. So before, we had Scavenger in the stop the world, and the difference here now, Scavenger is going to be running concurrently with the application. So it's still a generational copy collector. We now have to introduce a read barrier because now we're going to be moving objects concurrently with the application. Before we were just marking objects concurrently, now we're going to be moving them as well. It is a pauseless GC. Like I said, it's very similar to ZGC Shenandoah in the sense that they have the same goal, but they're still a little bit different implementation-wise. The heap layout still the same of GenCon, new space, old space. In the new space, we have allocate and survivor. And this is how the application behaves. White arrows, again, application thread, and in red, the GC thread. So the yellow threads represent the GC threads running concurrently with the application. So here we have two stop the road pauses, very short one at the beginning of Concurrent Scavenger and one at the end of Concurrent Scavenger. So the one at the beginning is for us to traverse the routes, find the routes, and then once we have that, we can let the application thread running with the GC threads. So the GC thread is going to be copying objects as the application runs. And once the GC thread is done, then Concurrent Scavenger has another stop the world at the end just to bring all GC threads to synchronization so that the application thread can continue from there. So that's the main difference here. Scavenger is running concurrently with the application, whereas before it wasn't. And there we have another Concurrent Scavenger. And the way that we collect the tenure, the old space, hasn't changed at all. We still have the global marking phase here. We're still collecting the tenure concurrently, just the way we did before. All right, so here, like I said, we have multiple GC threads trying to move objects, and we have the mutated threads trying to access the same object, right? So you can imagine a lot of things can happen here. So let's think about the situation, right? We have two threads here. Is the GC thread, and the other is the mutated thread. So GC thread is trying to move the object because that's what GC is trying to do, right? Collecting the object. And the mutated thread is trying to modify a field of the same object, right? So what would happen here in this case, right? There's a race condition here. So the way that we deal with this is that we unconditionally copy the object. Both threads will copy the objects, and then they're going to race to install the forwarding pointer into the original object. And whoever loses it, no matter, because since they both were copying since both have already copied the object, the one that lost can use the forwarding pointer to access that object. So this is how it works. So both threads is going to unconditionally copy the object just like that. And at this point, they're going to race to install the forwarding pointer. So in this case, GC thread won the race. So GC thread installed the forwarding pointer, and mutated thread is going to be, okay, I lost, but no matter. I see a forwarding pointer here, so I'm going to follow that and access the destination object. I'm going to get rid of my copy and use that two-space variant from the GC threaded copy. So here we have a strong two-space variant where all modification has to be done in the to space, not in the front space, which is kind of nice because that way we don't have any race conditions, and we have a consistent view of the heap. So that's Concurrent Scavenger, GenCon Concurrent Scavenger. Now let's go to Metronome. So Metronome is an incremental soft real-time collector. It provides an upper bound on GC pauses. So here this is a very cool collector because on a window of 10 milliseconds, it is going to dedicate 70% of that time to the application, and 30% of that time is going to be dedicated to the GC. So this 30%, which is 3 milliseconds out of 10, right? GC is going to be, okay, I can do some work, some GC work, or I can give some milliseconds back to the application, right? To do some, so if I'm done in 2 milliseconds, right, what I'm going to do in 1 millisecond, just give it back to the application. So this is provides an upper bound on the GC pulse times. Here we have a different write barrier, snapshot at the beginning write barrier. And because of this barrier, we have a high percentage of floating garbage. And you're going to see why. So here, instead of dividing the heap into new and old space, we actually have region-based GC. And here we try to have 64 kilobyte regions. So the bigger the heap, the more regions we're going to have, because the regions are actually a fixed size, which is 64 kilobytes. Here we have what we call cell size based allocation. So a nice characteristic of Metronome is that all objects in a region is going to have the same size. So there are ups and downs about this. That's a really good, really nice characteristic about this. All objects in the same region is going to have the same size. No, this is not generational, right? But objects are going to have the same size. Objects can actually span multiple regions, right? With exception if the object is larger than a region, we're going to throw an out of memory, with exception of arraylets, which arraylets are just large arrays, large enough arrays. Say, and a large array is an array that is larger than a region. In that case, we're going to chunk the array into different parts. We're going to put a part here, another part here, another part here in the heap, and we're going to have the array header point to these different parts, which is just a clever way of storing large arrays into a region-based collector. So how Metronome behaves is a very, very simple collector. So I'm just going to cruise through here. So you see we have all these little GC cycles. This, what you see here, is a one cycle, and all these different red arrows represent one GC increment. So if you remember from the first policy I talked to you about up throughput, we have one large top-of-the-road pause. So imagine we take this one large top-of-the-road pause and divide it into little increments. It's pretty much what Metronome is. So Metronome is going to do some work here at the beginning, then we let application run, do some other work, then a little bit more work there, a little bit more work there, and so on. And that way it does in such a way that won't ever surpass those 30% in that 10 millisecond window, so that it can have the application has the feeling that it's running as a pauseless collector, right? So the barrier about this Metronome, because we're going to be marking objects concurrently as well. So, but here we have another barrier, which is called snapshot at the beginning barrier. So because of that, it causes a lot of floating garbage, and the barrier has to be performed before they store. So how does the following object graph? Let's assume GC thread has already marked the roots. Object A is in the middle of processing object B, and hasn't seen object C, neither D. And then application thread comes along, adds a reference from A to D right there, and then deletes the reference from B to C. And it's at this point that the barrier is triggered, because if the barrier wasn't there, we would end up with object graph like this, and we would lose object C, which is fine because C is not reachable from anywhere. but we would have lost object D. And the way we remember this is that instead of having a resulting object graph like this, we will have something like this. This is how the barrier is implemented. So we put the field in the temporary. If the barrier is active, we remember that. So we would have the resulting object graph like this. And you see, the object C just happens to be in the way of object D. So because we didn't have to remember object C because it's garbage, and because of that, this is object C is considered floating garbage. And that's the snapshot, the beginning barrier, which is triggered whenever we delete a reference, object reference. Now, the last but not least policy is balanced. If you're familiar with G1 from Hotspot, they are very similar to each other. They're both they're both region-based. They're both generational. One difference that I can think of is that balance have 27 ages, I think, and the Hotspot G1 has 3 different ages. But both are, so they are region-based generation collector. It provides significant reduction in stop-the-roll pause times, introduce a write barrier, because similar to GenCon, here we can have multiple references from multiple regions going to this one region here, and we need a way to remember that. And there's a really cool thing about this is this heap defragmentation, which I'm going to show you with a really cool graph in a little bit. So here the heap, similar to Metronome, is divided into regions. But here we try to have 2,000, between 1,000 and 2,000 regions. Therefore, the bigger the heap, the bigger the region. Here, region is going to have ages, right? So every object on the same region is going to have the same age. Objects are put in what we call add-on regions, which is pretty much another name for new regions. And if an object is larger than a region, we just throw an out-of-memory error, with the exception of arrays. And similar to Metronome, we chunk this array into different parts and call them arraylets and put it to different regions in the heap. Cool. So this is how balance behaves. Application thread starts when we hit a threshold of, so when we deplete these new regions, right, we trigger what we call PGC. So PGC stands for partial garbage collector. So partial garbage collector is very similar to Scavenge, is a copy collector, which is going to be copying those objects from the new regions to another region. So the way it does this, it looks for those best regions to collect. So meaning, say you have a region which only has one live object. All it has to do is copy that one live object to another region, and voila, we have an entire free region. So it tries to look for those best return of investment regions. But there's a downside to BGC. It only has local information about the regions. So with time, it's going to lose this information. So we need something to update that information. That's where GMP comes in. GMP stands for Global Marking Phase. And GMP is not collecting objects, it's just marking objects. So it does that because it has the global information about the entire heap. And once GMP is done, it's going to update PGC information. So PGC, once that happens, when GMP updates PGC information, it's going to have the most updated information about the heap. Therefore, it's going to be able to make better decisions in what regions to collect. And that way, they communicate that way so that it can collect objects in a more optimized manner. Now, GMP, again, which stands for Balanced Global Mark Phase. It does not reclaim any memory, right? Just before marking. It's scheduled to run between PGCs. It doesn't affect PGC at all. And it's going to build an accurate mark map of the whole heap. And this is the thing, this metastructure mark map is going to be used to update the PGC mark map. And because of that, PGC is going to be able to make better decisions in which regions to collect. So this is a visual representation of how balance behaves. So on the x-axis, we have the time. On the y, we have free heap. So lines going up is the PGC collecting the heap. Lines going down is the application consuming memory, right? So you can see this trend going down, and if that trend continued, right, we would hit out of memory error. And that trend goes down because PGC only has local information about the heap and loses that information over time. So GMP is smart enough to trigger at that point so that it finishes in a timely fashion to update PGC, and then once PGC has the most updated information about the heap, it starts to defragment the heap, which is why you see this trend going up around the time 180. And then with time, PGC is going to lose this information, then you're going to see this trend going down again, and then GMP is going to have to trigger it again, and so on. So this part here where you see this defragmentation is really cool because GMP just updates PGC information, then PGC now knows how to defragment the heap. Cool. So right barrier, right? Remember I said there might be multiple objects in different regions pointed to a certain region, and we need a way to remember that because PGC alone is not able to do that. So here we need a right barrier. So it's a very simple barrier here. So it's an unconditional barrier. So every time we set a field of an object, we dirty that card unconditionally. And then the beginning of a PGC, GC thread is going to check for those interregion references and try to see if there's an interregion reference and remember that object. Because here is a trade-off, right? So here we chose to put the burden on the GC thread other than the application thread, because if we put the burden on the application thread would have to every time check for interregional references, and then it could be expensive, and then go to the slow object path and all that, right? So all it has to do here is unconditionally dirty the card, and then GC takes care of the rest. Cool, so that's all for policies. Now I'm gonna go quickly of a really cool thing that we have in OpenGL9 balance is called double mapping. First, I'm gonna talk more about arraylets. So like I said, arraylets are just a clever way of storing large arrays in region-based GC, right? And what we do is just chunk the array into multiple different parts and put in the heap. This is how it looks. So in the bottom there, we have what we call the array header. In the header, we have the class and array size. And after that, we have the data references to the array, which we call arrayoids internally. So here we have 3 arraylet leaves, meaning all the arraylet data is going to be residing on these arraylet leaves, which is the blue regions in the heap there. So imagine we want to access the first element of this array. How will we do it? So we would go to the first arraylet leaf, which we would follow that first pointer there on arrayoid, which would take us to the last blue region there, and that's where the first array element is going to be residing, right? So that's you see how we chunk the array into different parts there to put that into different parts of the heap, as opposed to having this just large contiguous representation of the array that could go in the heap. So this is what arraylet are. Now, some APIs require a contiguous view of the array, which is not the case for arraylets, right? Because they are all over the heap. So if you're familiar with the Java native interface, critical APIs, it's used when a programmer wants direct addressability of the object. And because of that, we need a contiguous representation of the object, which is not the case of arraylets, right? So what happens, right? What used to happen, at least in this case, so if there is a call to J9, we used to make a copy of the array, a temporary copy. Then we would copy element by element to this temporary array, right? And then we pass this temporary array to the API. The API could modify some of these objects, right? Does whatever it has to do. And then at the end, we'd copy everything back. And yes, as you can see, this is very expensive, right? So double mapping to the rescue. So the idea here is we want to make these contiguous arraylets look contiguously in memory. So everybody knows that physical memory is very limited, but virtual memory is not, at least in 64-bit systems. It's actually 2 to the power 64, in fact, which is very, very large. So we can leverage that for this technology. So the trick here is we map 2 virtual memory addresses to the same physical memory address. And the nice thing about this is that any modification to the newly mapped address will be reflected to the original virtual memory and vice versa. If you're familiar with ZGC, they actually use this technology they call multi-mapping, and they actually do this for every object. And they do this because they do that to keep track of in which stage of the GC the object is. So they use this multi-mapping for that. And here we just do to make these contiguous arrays look contiguously. So this is how it looks double mapping, right? So in the bottom there we have the array header. And in this case, we have 5 leaves. So we chunked the array into 5 different chunks. And so we map that array in such a way that in memory, the second virtual memory is going to look contiguously. So for those APIs that require contiguous representation of the array, all we have to do is pass the address of this second virtual mapping, right? And that way is really nice because any modification there is going to be reflected in the original array and vice versa, which is pretty cool. And because of that, we got a 30 times boost in speed up whenever it comes to array operations. Cool, but double mapping arraylets is only available in newer versions of Linux because of the system calls that we have to do. And can we do better? We actually can. So as we speak, we are working on another technology called off-heap management, which is going to be, I would say, substitute for double mapping. And the good thing about this is that more platforms are going to be able to support this technology. And it's pretty much going to have a secondary heap where you're going to be putting these large objects, in our case, large arrays. So stay tuned for that. Okay, so we're almost at the end here. This is a quick policy guide for GC, right? So all the policies for OpenGL9 are there. Some characteristics of them, right? Some of them generational. Most of them are concurrently, with the exception of Throughput. And these different policies have different heap layout. I should have heap layout there instead of defragmentation, but yeah. So for instance, GenCon has new, old space, balance, metronome, region-based, right? And all these are concurrent with exceptions of Throughput. Here are some more characteristics, right? GenCon is very good for web servers, desktop applications. Balance, very good for large heaps. Metronome for an application that requires soft real-time system, right? And Throughput for very small heaps because it's going to have the highest GC poses, as you can see here. So it's going to have the highest throughput, and that's because it doesn't have to worry about read and write barriers, but it's going to have the longest poses. So there's a trade-off there, right? So if you do care about the poses, probably you should go with GenCon CS, which has the lowest poses, but it's going to hurt the throughput because of the read and write barrier. Okay, so this is a comparison between the most known policies out there. On the right, there are some of the hotspot and Red Hat policies, and on the left, we have the OpenGL9 one. So in the yellow there, we have the most common policies, in blue, poseless, and green is also poseless GC. So on the top there, we have GenCon CMS. So the line there represents some similarities between them, right? GenCon CMS, they both have old new space, they're both generational, they both have the copy collector. Balance and G1, they're very similar to each other as well. They're both region-based, both generational, right? In the bottom there, the lines are not as thick because they don't share as much similarities as Metronome and ZGC. They're both region-based, sorry. But they have very different characteristics. For instance, ZGC uses multi-mapping, right? Metronome has those soft increments, right? GenCon CS is not region-based, has the new and old space, but it's kind of similar to Shenandoah because both use the same read barrier. Shenandoah version 2 actually, because Shenandoah version 1 uses Brooks pointer, which is a different kind of barrier. And then on the green there, we have Verbose Gc from Azul. It does require some special hardware or software for that. So in summary, if there's something I want you guys to take out of this, and you probably know this by now, is there's no perfect GC that fits every workload, every benchmark, every application. But if you don't care about pauses at all, you should go for a perfect stop-the-road GC, which is the case of Throughput. Not sure if it's perfect, but it's going to have the highest throughput. If you do care about the pauses, you should go for a pauseless GC, right? That's because the objective of pauseless GC is to get rid of pauses at all. And if you want something in the middle, right, you can go with like GenCon, G1, Balance. Those are somewhere in the middle there of good policy. So different policies deals with heap fragmentation differently, right? Like I said, there's no perfect GC that fits all applications. And you notice that Throughput has the highest throughput, and that's because read and write barriers are not for free, right? They penalize the application with throughput. So, for instance, ZGC, GenCon CS, Shenandoah, they're really good. They have the shortest pauses, but also they're going to have the lowest throughput, and that's because of the read and write barriers. And that's all from me. Here are some links if you're curious to know about more OpenG9. OMAR is just another project that OpenG9 uses on this technology. Both are open source, and we welcome any contributors. And Adopt OpenGDK is the link to get the builds. That's it for me. Feel free to connect with me either LinkedIn or Twitter. This is the book. If you are curious to know about any of the algorithms, GC algorithms, this is what I call the GC Bible. Everything there is about GC, you can find it there. And that's all from me. Thank you all, and I hope to see you sometime.
Thank you, Igor. That's me, Andriy, and I will ask you a couple questions. Some of them are from our participants who are watching us through the YouTube.
Sure.
There are a couple questions, and but before we go to their questions, since we have a small delay between our stream call and the YouTube translation, I will ask the question from our side. So. Is there any, I don't know, plans or visibility to build a really non-blocking garbage collector who will work absolutely in parallel and don't have any impact on Java runtime?
That's what everybody wants. That's for instance, such as ZGC, Shenandoah, even us, we are actually working right now on another policy that we're going to try to tackle the perfect pauselessness, right? But that's really hard because you can maybe get rid, for instance, because you have to traverse the roots and, for instance, class objects. There's many nitty gritty details, bringing tries into synchronization and all that. So having 100% pauseless is hard. It's not impossible, but hard. For instance, I think it was Azul. They published a paper not so long ago, a while ago, of an algorithm that's actually proven to be 100% pauseless. So with their special hardware, they were able to do that. But we do require special hardware software. But yeah, we do have plans for that. It's hard. Hopefully someday we're gonna get there. But yeah, right now, ZGC, Shenandoah, and GenCon CS are the ones that try to reach there, but they are not completely 100% pauseless.
Okay, thank you for your answer. And the question from our participant, Olesya, she is asking, how often do you actually need to configure garbage collection by yourself? Is it say that you need to configure garbage collections only if you are an expert, as it is easy to make things only worse? What are your thoughts?
Well, you don't have to be an expert on whatsoever. It's good to know like what's out there. For instance, it's good to know, for instance, what JVMs out there, what different policies out there, because like I said before, it's there's no perfect GC that's gonna fit every application. Like I cannot tell you, just go with this. Doesn't matter what application you run, this is gonna be the best, right? So what I recommend is just trying different policies and to tune them, right? There's some really basic tuning, for instance, max heap size, min heap size, max nursery size, those kind of things, right? So you can see more or less how your application behaves with different policies, with those little GC tweaks, I would say. And in order to better see what's going on with the application, both JVMs have what we call the Verbose Gc option, right? And the nice thing about, I'm going to go back to OpenG9 here. We have verbose.gc, and you can use this verbose log to visualize. So if you remember the graph that I showed you, the balance graph that shows like the behavior of the balance policy, that's how I got that graph through the Verbose Gc, because we have a system called VMGC, which is a GC visualizer, right? So you can get that log and visualize how that application behaves, which is really cool, right? The hotspot has Verbose Gc as well, so you can see like how long are the pauses, and how much time each application is taking, right? But with this GCMV thing, you can actually see a summary of your total application, which is kind of cool. And it's also going to give you some suggestions as to, like, we noticed that the GC is spending too much time doing such thing, right? So you might try this, right? So in that sense, it's really cool to help. It helps you understand how your application behaves.
Okay, thank you. Actually, you, I guess, almost answered the next question, but anyway, I will ask. It's from Max. He asked, which tool do you use for monitoring garbage collection activities? I know a few of them, but maybe you can say which is better. And you mentioned about GC visualizer, so probably that's your own tool, or anything else?
I'm not sure if there's something similar for Hotspot. I'm sure they do have a verbose option, but for OpenG9, our verbose is very verbose, and you can use that with this GCMV technology. And it's just very simple. It's a plugin in Eclipse, right? If you have the Eclipse IDE, you can just go to the marketplace, type GCMV, download that, and you can just put there the GC logs from OpenG9 JVM, right? And then you will see there the summary, and you can plot the graph, like how often the GC is collecting garbage, and it's really cool. We use this pretty much all the time here to see how our GC is behaving.
Okay, cool. And there are one more point from Oleg, but it looks like not a question, but probably just to hear your thoughts. So the point is, would be nice to have some online tool that can suggest most suitable GC for your application based on properties you select.
So, yeah, I actually thought about that a while ago as well, because the graph that I showed you before, not graph, the table, right? For instance, GenCon CMS is good for web servers, and then you have Metronome is good for real-time applications, or Balance, which is good for large heaps, right? But so those are really high level, right? Like large heap, web server, real-time GC, right? But then when you start to, because maybe your applications are going to be very aggressive about allocating objects. Maybe your application is not, or maybe you don't care about the pauses, which in that case, right, you can just go with GC that of throughput, which doesn't care about pauses at all, right? So there's many little details that an application can have that I don't know. I don't know why there's not maybe a well-known, let's say, advisors there. Probably there is, but I think it's because of there's so many different workloads out there that little tweak can make one GC better than the other, right? Maybe because of that, there's no such like one place to go to say, okay, this is the guide to go. But the guideline that I give you is just a high level, right? Then you have to look into the actual workload and how they behave to actually piggyback which policy is best.
Okay, thank you. I don't see any other question on YouTube channel, so I guess that's it. So thank you so much. That was really interesting and useful. Right now we will switch to the maintenance window, and right after a few seconds we will have a closing ceremony.
Awesome. Thank you so much. Thanks so much for having me. Bye-bye.
Okay, so thank you everyone for joining this online session. So many thanks to Igor. I know that it's like online talks always pretty complicated. It's not like real life talks, but thank you so much, Igor, for doing it for us, for our community. And actually, Java and the garbage collection is a really important part of its ecosystem. So thank you so much. Thank you to our partners, Avenga and Sombra. And thank you to our community partner, JetBrains. Please fill in feedback forms and you will be in the list and have a chance to get the free license for the 1 year. Thank you, everyone. Join us, follow us. We will do more events in future. You know, actually our policy, we do it once a month. So stay up to date. Have a nice evening. Bye-bye.